Okay, good morning, everyone. Okay, so let's wait a few more seconds for everyone to join. Okay, so let me start with some administration thing. I'm going to respond to the question on the chat just when we're done with this. So first of all, yes, so remember that all the lectures are available, including the new set of written notes. So it's on the website. You will find it there in a green box just across from the lecture notes for lecture 4. And if you open this PDF, you'll see at the top the code that I used last time. You can run it as Colab or you can download and run it locally. Okay, so that's one important note. Please do go over the lecture notes. As I said, I always update it a little bit immediately after the lecture, but it's already pretty good approximation is available before the lecture. Okay, homework 1, we made an effort, or TAs made a lot of effort to grade it very, very quickly, so that you'll have it just in case a few of you want to look at it as a criterion for deciding whether to stay in the class or not. Today is today or tomorrow, I guess. It's a drop date. You can always drop classes later by appealing, but this is what makes things easy. So just wanted to say that the results were actually very, very good. So I show here the average of homework 1, 90.5 out of 100. With extra credit, even a little bit more. You can see the distribution this way. Here I'm including also the extra credit, so it's out of 125. And I think that all of you did really well. If you got less than 80, you definitely want to check why you got less than 80. But other than that, I think things were as expected. Please do ask questions. If you have, go to the office hours, ask on Piazza, so the TAs will explain to you if you have misunderstanding or any concerns with respect to the homework. Okay, a few other things. Homework 2. Hopefully you all saw my Piazza message last night. We decided to extend homework 2 by 3 days, so it's going to be due on October 22nd instead of the 19th. If it's not already on the website, we'll update the website accordingly. There is no class on Wednesday. Again, I announced these 2 changes yesterday. The reason was basically a discussion among faculty that got the feeling that the classes this semester, because of this weird format we are all in, are more stressful than usual. I guess in some classes, I don't think we are in this situation, but in some classes, people run way too fast because it's easier to run too fast when you just talk to a monitor rather than to people. So hopefully this kind of 1 day off will allow you to catch up if you're not caught up, take a little bit of a break, and you will get more time to complete the work. If you do have questions on this, let me know. Send email, use Piazza. just one thing to make sure that we're clear. So we extended it to 1022. On top of it, you still have the 4 late days. This will bring you very close to the exam. So I do suggest that you'll try to finish it earlier, so you'll have a few days to deal with the exam, with the midterm exam. Now, we have not changed the quizzes at all. Quizzes are still, a quiz is still going to be out. And the quizzes are going very well from my perspective. Do let me know if you think differently. So again, looking at the score from yesterday, I think all of you did really well. So the average was something like 96%. Take some time to come up, but 95%. And about all of you did it. So 134, 135 of these students did it, which is good. Okay, one final comment, midterm. You all know that midterm is coming. The midterm is going to be at the class time. So we'll plan it to be an hour or maybe an hour and 15 minutes, we'll see. Now, some of you, very few of you have a serious time zone problem. Please email me if you do, and we'll find another solution. A few of you already, I already got emails that you need more time than the time allotted here. Again, send me email, we'll be in touch, and I'll tell you how we're going to handle it. Okay, recording. Yes, we are recording. Any questions? So hopefully I answered the first question about the example from last time. Yeah, answers are going to be available. If they're not available already, they'll be out today. There will be several practice midterms that we'll make available. Let me say one thing. Given the fact that we are at different times now, unfortunately, we're going to give you practice exams, but the style of the exam this semester is going to be different. So typically we would give 4 or 5 problems that take a long time, or relatively a long time. This time the exam is going to be more in the style of the quiz questions. So there's going to be more questions and they're going to be much, much shorter. Any other questions?
Will they be choice?
Oh, sorry, go ahead.
Yeah, go ahead.
Will all the questions be multiple choice or will they be free response?
I don't know yet, but I think all of them will be multiple choice. That's the current plan, at least. Another question?
Yeah, is there a way for us to check if we are registered on Polev? Because I realized that I'd been answering anonymously. So I'm wondering how I can rectify that. I think I'm registered now, but I've been answering previously. And I don't record it.
So send a Piazza note or email to Ryan, who is monitoring this,
Perfect.
and he'll be able to help you.
Okay, thank you.
Okay, so let's move on. Where are we? So we talked about online learning the last couple of weeks. Basically, the learning paradigm we are working in is we are observing examples, a stream of examples as they come, and we are updating the hypothesis after each observed example. Specifically, we started last time to talk about one important instance of online learning, Perceptron. And Perceptron is special also in the sense that it's a mistake-driven algorithm. So we update the weight vector only when we make a mistake. Now, today we're going to continue with Perceptron, continue with some variations of Perceptron, and also try to understand this algorithm as a special case of a general family of algorithms that you've already know for a long time now, SGD, stochastic gradient descent. And then move on to talk about some more update rules and a few other important concepts that we are introducing in the context of online learning, but they are important more generally. Okay, just to remind you, Perceptron, we talk about a function from x to y, where y is plus minus 1, and x could be either a Boolean vector or a real valued vector. We only learn a weight vector. So really our function is defined by this weight vector w, and the way we make prediction is we compute the dot product w transpose x, and we take the sign of it. That is, if it's positive, it's +1, otherwise it's -1. Given a set of m examples, x1, y1, up to xm, ym, this is how we run the algorithm. We initialize the weight vector randomly, for example. We go through all the examples, predict the label according to this prediction rule. Our prediction y prime is the sign of the dot product. If we made a mistake, if y prime is different than the gold y that appears here next to each x, we update the weight vector. And we update it this way. We add to the w, to the weight vector w, r, which is a constant, think about it as 1 now, times y, which is the label, the true label, times x. Which basically means that if the example is positive, we add x to w. If the example is negative, we subtract x from w. Very simple. If we don't make a mistake, we don't change the weights. Very simple algorithm. I'm writing it here in a slightly different, oh, okay, so I did show you this example. I'm not going to go over it today. I ran through this example. I also ran through some code. Go to the code, play with it, make sure that you understand the algorithm. I also showed another way of writing the algorithm, where the difference here that here I'm distinguishing updating W and updating theta. So sometimes you'll see it this way, also in your homework. Sometimes you'll see it all compiled into one update because we already put the theta into the last dimension of W. This is how I did it in the code that I presented last time. Okay. And again, the reason I put this way is just that you will not miss the fact that we always update both W and the threshold. We either do it separately or we do it by putting them together, concatenating the theta as the last dimension of the W. Okay, so now that we are done here, at the end of last time, we talked about the mistake bound theorem. This is really a key result, very classical and very important result that basically says, surprisingly, that Perceptron is going to stop making mistakes. We talked about it last time when we said, if we have a finite hypothesis space, a finite number of functions that we are entertaining as candidates for our hidden function, it makes sense that we stop making mistakes sometimes. But if we have an infinite hypothesis space, as we have here, because all weight vectors, infinitely many of them, could be candidates for the hidden function, then maybe it doesn't make sense. Maybe we'll never stop making mistakes. So it turns out that under some reasonable assumptions, we are going to stop making mistakes, and Perceptron is doing it. So this is a result from the 60s. Novikov was a Russian mathematician. And this is what it says. Again, we are starting with a weight vector. I'm going to assume here, just for the proof that I will not show, that just for convenience, that the initial weight vector is all 0. When we get an example X, which is real valued vector, we are updating, we are predicting according to this rule and updating according to Perceptron. And the theorem says this. Let's assume that we got this sequence of examples. And we are assuming here that the size of xi is bounded by a constant r. I'm reminding you here something that I'm sure you already know. What is this notation? This notation is the size of a vector. I'm using it twice here for x, for the ith example, and also for the vector u. It's also called the L2 norm, and that's the definition of it. Well, okay, it's not the right definition, unfortunately. I don't know what happened. Should have been squared and square root. Okay, we'll fix this later, but not sure what's happening here. A few subscript and superscript disappeared, but basically the size of the vector. Now, one question that I want to ask is first, so I make this assumption here that all the examples xi are bounded in size by r. Is this a big assumption? Is this always happens? Or is it something that I make an assumption and only because of that we can prove this theorem? We can bound the mistakes. Anyone wants to take a risk here? Okay, so one answer here that it doesn't always happen, but we can normalize input. But let's assume I don't normalize input. I'm not changing the input at all. I don't want to normalize because it's costly. I just want to take the example as is. How many examples do I have here? I have a fixed set of examples, right? T examples. Each one of them has a size. And therefore, they also have a maximal size. I'm going to call this maximal size R here. So it always is the case that I can say that there is this R that bounds the size of all the examples I've seen. Okay, so there's no assumption at all. It's just a notation. I'm calling R the largest size of all examples I've observed. Okay? So that's one assumption. I'm also assuming that there is some U, which I'm going to call the truth. And there is some positive gamma, such that the size of U is 1. U is going to be the truth, which is the true vector, the true hidden function we're after. And I'm normalizing its size so that I can always say that it's 1. Basically, I'm dividing U by its size, and now its size becomes 1. And then I'm assuming that for all examples xi's, yi times u dot product with x is greater than gamma. And this is something that some of you who've read the homework carefully already know, but let's try to decipher this. What does this say? So let's assume that y is positive. It's a positive example. Then this says that the dot product u times xi is greater than gamma. If the example is negative, then it says that u times xi is less than minus gamma. So basically, that says that the examples are separated by some margin, gamma. The positive examples, the blue one here, are gamma away from u, and the negative example are also gamma away to the other side from u. This is really the meaning of this. And this gamma, we can think about as a complexity parameter. It tells us how complex this data set is. Are the positive very separated from the negative, or they are very close together? Now, I tell you that this data set is linearly separable. That is, this U exists. Once I told you that this U exists, I would argue that this is not a big assumption. This gamma also always exists. Why is that?
If they're linearly separable, then there has to be a minimum distance between the closest to the separator.
Exactly. So I'm just looking at these T examples. I know that they are linearly separable. So there is a U in between, and there is a positive example that is the closest to U from this one side, and a negative example that is closest to U from the other side. And these together define my gamma. So there's always a positive gamma that separates the worst positive and the worst negatives, if you want. So basically, I didn't make any assumptions here. I just invent a notation which has to do with the size of the example and with the level of separability, the margin. Under these conditions, one can show that the perceptron makes at most R square over gamma square mistakes on this example. What is important here? What's important here is that the number of mistakes we're going to make is inversely proportional to gamma square, which makes a lot of sense, right? So if gamma is very, very small, which means the positive example are very close to the negative example, then I'm going to make a lot of mistakes until I manage to place a separator between them. If, on the other hand, the positive example and the negative example are very far from each other, that is, gamma is big, the number of mistakes is going to be small. It's going to be very quick to place the example, the separator there. So really the important thing here is that one, we're going to stop making mistakes, and two, the complexity parameter that dictates how many mistakes we're going to make is this margin, which is a really important concept that we're going to see a few more times. Okay. One comment that I want to make. So I'm not going to give the proof of this theorem, even though it's very easy. It appears on one slide in the next slide here. But I want to tell you that one important lesson, and in fact one goal of this class, is for you to be able to read math. So while I don't want you to be able to prove the theorem, I do want you to be able to interpret these kind of things. So machine learning is a very fast growing field, and what you learn today, hopefully the basic things that we're teaching in the class is going to stay with you, but you're going to use different algorithms, you're going to use different methodologies, and all these in the future, and all these will be presented to you in mathematical notation. So one of the key lessons that I want you to take from this class is how to read this mathematical notation, understand it, and implement it. So with that, as I said, I will not going to go through the proof, but I do want to make a few comments. One important comment is that this bound, which is this R square divided by gamma square, doesn't depend on the dimension, doesn't depend on how many dimensions W and X have, or so it seems at least. Because really the dimensionality goes in an indirect way into computing this gamma. No, it doesn't depend on the number of examples. It's really just the number of mistakes that we care about here. And that's important. So another important thing is that we are talking about weight vectors here and examples in the same space, right? This is what Perceptron does. It adds examples to weights. Everything is in the same space. Again, a very important thing that we're going to use again, hopefully at the end of this class or next time. And the final thing is it's important for us to understand what does the theorem mean. So as I said, we stop making mistakes, or perceptron stops making mistakes after some time. What does it mean? Of course, if you will give me an example here, in the middle, on the wrong side, perceptron is going to make a mistake. But we made an assumption. Under the assumption that the data is linearly separable with margin gamma, all future examples that I've never seen in training, but that satisfy this separation condition are going to be okay. I will never make mistakes on these examples that are separable with gamma margin. Okay, so let's questions on this.
Professor?
Yes.
So when yi is negative, I don't see why the projection of u on x. So like why the equation still satisfy such that the left-hand side is a negative number and the right-hand side is a positive number. How is that satisfied when
You're asking about this condition here?
Yeah. Yes.
So what does this condition mean? This condition means that the dot product. So remember, we are making prediction based on this, whether the dot product is positive or negative. Okay? That's how we make prediction, and that's how we decide whether we're going to update W or not.
Oh, okay, that makes sense.
Now, what I'm saying to you, I'm even more strict than this. I want the dot product for positive example, not only to be positive, but rather to be greater than gamma. And for negative example, I don't want it just to be below 0. I want it to be less than negative gamma. So I'm more strict. I'm separating the positive and the negative more than required by a margin gamma. Is that okay?
Okay, that makes sense. Okay.
Okay, good. So let's move on. So now that we understand perceptron, you can say, okay, but it's unrealistic to assume that the data is always going to be separable. I will get some examples, maybe in the future, that kind of go into this region. What's going to happen there? It turns out that the algorithm is quite robust. So let's robust to noise. And in this case, I'm thinking about noise as something that isn't separable. So let's see how can we even think about this notion. So in the non-separable case, I want to quantify the extent to which a data point fails to have margin gamma. So this is my margin gamma here, but this red point moved to the other side. This purple point went into the margin here, into the thickness of this linear separator. Maybe not to the other side, but still less than the gamma margin, and so on. So I want to quantify this, and the way to quantify it is using this slack variable, psi, and we're defining psi to be the maximum between 0 and gamma minus this sign dot product. So let's try to understand what that means. So if I'm very separable, let's take this red example here. This is very far from the margin. So in this case, y times wx is going to be very large, right? So it's on the right side, so it's positive, the product of the dot product and y, and it's very far, so it's even large. Same thing for this purple point here. The dot product wx is large, and it's on the right side, so this is very, very large, which means that gamma minus it is going to be very negative. So the max between 0 and it is going to be 0. So nothing is going to happen. Psi is just going to be 0. For all these points that are far away, psi is going to be 0. On the other hand, if you go into this region, which means this product, y times the dot product, is less than gamma, which means this guy is positive now. So the max between 0 and this is just this value. And of course, if I go to the other side of the line, it's even more negative, this guy, So this guy is going to be even more positive, this difference, and that's going to be the value of the max. So what have we talked about? What have we showed? That psi is 0 if the example is on the right side. It has at least margin of gamma. And otherwise, if it's within this region or goes to the other side, this is going to grow and go linearly with this value. So that's a way we quantify the lack of separability, the extent to which the example isn't behaving the way we want. Now I'm going to denote, so this is for each example, right? So psi I is a slack variable for a given example, for the ith example. Now I'm going to sum it over all my example, and I'm going to call D2 the sum over all my examples. Sum of squares, square root. And then the extension of the perceptron theorem is going to say that we're going to actually bound the number of mistakes we're making in a very similar way to before. So there is this R over gamma square that you've seen before, but now I'm also adding this slack variable. So basically that means that perceptron is expected to have some robustness to noise. So even if some of the examples are not separable, do not satisfy my condition, perceptron is going to be quite robust. And in fact, you're going to see this for perceptron and other related algorithms from this family in the homework that you'll do. Okay, so that's one important understanding. Now, here is just a comment that I find interesting and will drive a little bit some of what you will see in the homework. If you really go back to these junctions, right? So I'm going back to the kind of the simpler cases rather than general linear functions. Let's talk about these junctions. And you think about K disjunction. This is an example that we gave last time or 2 meetings ago. This is a disjunction, say, on n variables, where I tell you ahead of time, only K of them are going to be on. K is going to be much, much smaller than n. It turns out that despite the fact that K is much, much smaller than n, perceptron, and in fact, almost all the algorithms that you deal with are going to still make order of n mistakes, despite the fact where n is the number of features we have. Despite the fact that I told you ahead of time that only K out of these n are really important. You can actually play with it a little bit and try to convince yourself by finding a sequence of examples that will cause the perceptron to make order of n mistakes. The reason I mention this is because when we talked about the halving algorithm, we actually said that theoretically, it's possible to have a much, much better bound, K log n. Go back to this halving lecture and you'll see that we counted how many disjunctions are there. We took the log, and the log of these that we got from the algorithm was K log n. Now, think about it. K log n is much, much smaller than n, right? If n is 1,000, let's say log 2 of n is going to be 10. And if k is 5, we have 50 here as opposed to 1,000. And basically, long n is a much nicely behaving function than n. So this surprisingly can be achieved by Winnow algorithm, which is one reason you're playing with Winnow in your homework. If I have time today or next time, I'm going to show you some additional learning curves, interesting learning curve for these algorithms to basically drive home this difference between algorithms. Some of these differences have been neglected by the community in the last few years because people are too busy playing with deep neural networks. But some of these are actually quite important. in some regimes. Okay, so let's move on to some practical issues and extension of Perceptron. So there are many, many extensions that can be made to the basic algorithms, and I'm going to discuss a few of them. Some of them are necessary. I mean, so no one today is going to use the vanilla Perceptron, but people will use some extensions of it that we're going to discuss. One important issue that we're going to see in all learning algorithms, and I already mentioned last time, is we sometimes want to convert the output of Perceptron or any other learning algorithm to be a conditional probability. So we don't want just to predict with the dot product. We want to know what is the probability that y is positive. So last time I showed you this curve, which is the curve of the function where you take your dot product, and rather than predicting whether it's positive or negative, you do 1 over 1 plus e to the minus dot product. And now the threshold becomes whether it's greater than half or less than half, which is completely equivalent to whether the dot product is positive or negative. Now, one can do more than that. So I can put a small constant here next to the dot product. And this will allow me to make sure that this expression really behaves like a probability distribution. In practice, it may not behave like a probability distribution. And I want to tune A, and you can tune A on some development set until you're happy with the behavior of this curve, and it fits your understanding. And there could be some, this can be said in a more well-defined way. It really behaves like a probability distribution. So this is a trick that people use in order to kind of massage the output and get it to behave more like a probability distribution. Okay, in order to move to another extension of Perceptron, I want to think about the following learning scenario. So you're running Perceptron on a stream of random examples. H1 made a mistake on the first example it saw. Because it made a mistake, we update it. Now we move to H2. H2 ran through 9 examples with no mistakes. So I didn't change it. So I'm still using H2, right? We have a mistake-driven algorithm. Only made a mistake on the 10th example. So I updated it, and now I have H3, right? So H here is indicate, or the number here indicates the hypothesis that I've used in the course of training. So after I updated H2, it became H3. And then this also made a mistake at some point. I updated it to H4 and so on and so on and so forth. I got to H98. H98 ran for a long time on 999 examples with no mistakes, so I kept it. It made a mistake on the 1000th examples it saw. Only after 1,000 examples, I updated it, and now I have a new hypothesis, H99. Made a mistake immediately. So I immediately updated it, and I got H100. It ran through 9 examples, and I updated it after the 10th example because then it made a mistake. Now, I have no time anymore. I need to stop training and output and give you a final hypothesis that you're going to use in practice, in life. Which one will you output? Which of the hypotheses we've seen so far will you output? Question that you can answer. Will you output the final hypothesis, or will you do something else? Meanwhile, I see that on the chat, someone asked again, what is this R? And the answer is correct. It's the same R that we showed in the definition of the theorem, the perceptron theorem, the mistake bound theorem. The largest example that we have in the training data. Okay, so here we are asking, given this learning scenario, where we have to stop training at some point, we ran out of examples, which hypotheses are we going to take with us to use in the future? Some of you are still thinking. But hopefully the question is clear. Are there any questions on the question? Okay, so let's see what you're thinking. H28 is the biggest one here. And some of you say 1,000, which I think by that you mean H28, because H28 was the one that survived the most. H100 is also pretty big here. Okay, so anyone wants to justify H100 or H98? Remember again, H100 was the final hypothesis that I had. H98 goes back to hypothesis. Is there a reason to prefer H100 over H98 or vice versa? Well, if you want to open your mute, then answer. Please unmute yourself only if you want to respond to this question. Again, any reason you would prefer one hypothesis over another? Okay, so someone suggests H98 to avoid overfitting. Anyone wants to elaborate? You can unmute yourself and respond. Another suggestion here is that H100 is biased toward the last few examples, so H98 is better. And both these answers are correct, and they are talking about, they are going in the right direction. So the key issue is that H98 is the most stable hypothesis we have. It survived 1,000 examples. So basically think about it this way. You have a hypothesis. Forget how we got it. H98 is a hypothesis that saw 1,000 examples and made no mistakes on them. H100, on the other hand, is another hypothesis that saw only 10 examples and made no mistakes on them. So I would always prefer a hypothesis that was stable and was good, was predicting correctly on a large number of examples. And that's a really important intuition, and that's the intuition that really leads to average perceptron. Some of you have already played with it because you try to work on homework 2, and I'm going to give some more details now. So really the motivation for this is that in real life, we really want more guarantees from the learning algorithm. In the mistake bound, we don't know when we're going to make mistakes. We're just going to know that we are going to make mistakes, but at the end, we want to choose a hypothesis that is going to be stable, right? So we want something that is consistent with as many examples as possible, because that's how we're going to use it. So ideally, we want to quantify the expected performance of a function over a number of examples rather than the number of mistakes. We really want a global guarantee. This is what we're going to get to in a few weeks when we talk about the PEC learning model. But luckily, and one reason we like to think about mistake-driven algorithm and online algorithm in general is that every mistake-bound algorithm can be converted efficiently to yield such a global guarantee. And the way to do it is exactly the way we discussed with this example, which is to find this hypothesis that is stable over a long stretch of examples. So the simple way to think about it is the following one. Start to run your mistake-driven algorithm. Wait for a long stretch without mistakes. And there must be one. Think a little bit for a second. Why is my claim here correct? That if you have a mistake-bound algorithm and you run it over the examples that you see, there must be some long stretch, as long as you want, without mistakes. Anyone is not clear about it? Why I will always have a long stretch without mistakes when I have a mistake-bound algorithm? Okay, I guess it's clear. Otherwise, you'll ask. So once I do find, let's assume I say, you know what, once I see a hypothesis that does well on 1,000 examples, I'm happy, I take it. So I need to wait until I have this hypothesis, and I'm telling you here, there must be one. If you care about 2,000, there must be one also that will have a long stretch of 2,000 without mistakes. And if that's your criterion, then wait until you see this, take the function, and use it. And this function that was consistent for a large number of examples is guaranteed to have this global good expected performance. Now, what we do in average perceptron is something a little bit more efficient than that. We're not going to wait until we have a long stretch. Instead, we're going to return a weighted average of earlier hypotheses, all of them, where the weights are a function of the length of the no mistake stretch. So we're going to average the hypotheses. Those that did not survive many examples, did not survive a long stretch of no mistakes, are going to have low weight. Those that survived are going to have high weight. And this average is going to have some very nice properties that we're not going to prove, but I promise you it's going to behave nicely. So let's formulate this algorithm now. So what do I have here? I have M, which is the number of examples I see. K is the number of mistakes I'm making. Ci is going to be the consistency count for the hypothesis Vi. I'm denoting my hypothesis, the weight vector, the consecutive weight vector that I see as VIs. And capital T is going to be the number of epochs. So here's my training examples. The output of this is going to be a list of weighted perceptron or weighted weight vectors. So the weight vectors are V1 up to Vk. Why do I have K here and I have M here? Why do I have K hypothesis?
We have different hypotheses when only when we make mistakes?
Exactly. So once I made a mistake, I move to another weight vector. So the number of weight vector I will have is the number of mistakes I will make. And it has nothing to do with the number of examples, right? Okay, so I'm initializing with k equals 0. The first weight vector is going to be 0, and my count, my consistency count is 0. I'm running over all my examples. I'm predicting with this dot product. If my current weight vector is vk, then I'm predicting that y prime is the sign of the dot product vk transpose xi. If I did not make a mistake, I'm just increasing the count, my consistency count. So vk got another count. ck grew by 1. Else, I'm updating. What does it mean to update? First of all, I need to update the weight vector. So this is the Perceptron rule. Vk plus 1 is Vk plus y times x. Standard Perceptron, I'm assuming here that the learning rate is 1. And I'm also initializing my consistency count. So now for ck plus 1, I have a consistency count of 1. And we continue. So this allows me to generate this list of weighted weight vectors, if you want weighted perceptrons. At the end, I have this list of weighted perceptrons. I have a new example, and I'm predicting by averaging this dot product. So for all I, from 1 to k, I'm computing vi transpose x. I'm multiplying it by the count, and then I'm taking the sign. Now, I left something, deliberately, I left something out here, different than the way it's written in your notes and different than the way it's written in the title here. I call this average perceptron. And that's how I make the prediction. Is it right? Is it wrong?
I think it's fine because you're taking sign.
Exactly. So that's I wanted you to think a little bit about it. I did not divide by the number of mistakes because it doesn't matter, right? So I'm taking the sign, and whether it's CI or CI divided by 17, doesn't matter, doesn't change the sign. So this is going to be the right prediction. And now to the question in the chat, if, again, the question is about updating the consistency count. So if I don't make a mistake, I'm increasing the consistency count, because I want to know how many times did VK survive without making a mistake. If I did make a mistake, I don't update CK anymore. I'm done. It already counted the number of mistakes I've made, and I'm initializing CK plus 1. You could argue that I should have started it with 0 here. Doesn't matter whether it's 1 or 0, but basically I want to start a new consistency count. Questions on this?
Are you shuffling the examples ever?
No. Of course, in practice you could, but it really doesn't matter because you're going to run over these examples many times, so the order will not matter. The order, if you just run once in an online algorithm, the order of the example could matter a little bit. But realistically, because you're going to run over it many times, it doesn't matter.
Thank you.
Okay, so of course, the same idea can be run on top of any online mistake-driven algorithm. And in the homework, you're going to run it on several algorithms, 3 different algorithms. And now notice that I'm kind of giving you an implementation here, but you will find that if you implement this in a straightforward way, it will take a long time to run. So you'll have to be a little bit more sophisticated with your implementation in order to get an efficient implementation. And that's, again, one of the things, one of the challenges is in homework 2. I really would like you to think about it, experience the fact that sometimes efficiency is essential. In fact, if you don't implement it right when you run it on the large data set in the second part, it's going to take a long time. So you want to think about an efficient implementation. Okay, and really this idea of averaging perceptron, which now comes with global guarantees, is as good as any other linear learning algorithm, if not better. So comparison of it with any other linear learning algorithm, logistic regression, or support vector machines, algorithms that we're going to address a little bit later in the class, show that this is as good as all others. So very simple algorithm, but a very, very good learning algorithm. Okay, so a few other bells and whistles that we want to talk about. We talked about the value of margin, the fact that we actually want to find not just a linear separator, but actually a thick linear separator, something that will separate pluses and minuses as much as we can. And in fact, you can actually encourage Perceptron or any other algorithm to do it if you say, you know, I'm not going to update weights if the dot product is less than theta or greater than theta. I'm going to add this other gamma here and promote the weights and demote the weights, that is, increase W by X or decrease W by X, not only if I'm greater or less than 0, which is what's written in this part, but rather greater or less than gamma. So that makes you a little bit stricter. Now notice here that this is different than what we're going to talk about later on when we get to SVM, because this gamma is what is called a functional margin. It's just a constant. And if the W's become very, very large, as we add access to them, as we train over a lot of examples, the value of this fixed number is going to diminish. Nevertheless, it found that experimentally that this actually helps. And it's a quite effective modification to the algorithm. Another extension. This is a question that you actually thought about in the quiz. Assume that you made a mistake on example X. Then you see example X again. Will you make a mistake on it? Most of you have concluded correctly that it's quite possible. The fact that I saw an example, the example was incorrect, I changed my weight vector, in this case from here to here, does not guarantee that I will not make a mistake on this example again. If you do want to not make this mistake again, you can simulate running on exactly the same example multiple times until you stop making a mistake on this example, at least for now. Maybe later on, because of other changes that you'll make, you'll do it again, but at least you can run consecutive multiple times on this example until you move the weight vector enough to not make a mistake on this specific example. Now, rather than running consecutively many times on these examples, you can actually do some linear algebra and do an update that is what we call threshold relative update. So instead of adding 1x, you're going to add r times x, where this is r. And basically what I did here is I solved a simple equation. You can try to do it yourself. That told me how many times do I have to update on this example r until I will not make a mistake. So again, this is an exercise for you. Think about how to pose this as a question, and then it's just a very simple algebraic equation to derive this r. Okay. So far, we talked about online linear learning algorithm, SGD, and Perceptron especially. And we also talked about the difference between them. And hopefully, I'm not going to let you answer now, but hopefully you understand that the difference between them is that SGD updates every time. The weight vector is being updated every time. And Perceptron updates only when it makes a mistake. So far, so good. However, this is true only because the SGD that we introduced in class, at least, was a very specific SGD, because SGD is really a family of algorithms that is parameterized by the loss function. We gave it at the beginning of the class for LMS, least mean square, but you can run SGD for any loss function that you like. So the behavior that I just quoted, SGD on LMS is making mistakes every time, is making an update every time, may not be true when you use a different loss function. So now what I want to do is I want to move one level up and think about kind of the general stochastic gradient descent algorithms, not with just with LMS, and see what interesting finding we have. So let's go back to the stochastic gradient descent algorithm that we discussed. We're given a sequence of examples. They are taken from some distribution over x cross y. We're trying to learn a linear, and this linear function is parameterized by this weight vector w. The goal is to minimize this expected risk function, right? So the performance on the training data on our M examples, where this is the expected risk, and this is the loss function Q, right? The loss function is a function of x, w, and y. I'm denoting here x, y by z. So it's still x, y, and w. And I'm averaging it over the examples. So in stochastic gradient descent, we approximate this minimization algorithm, this expectation, by incrementally updating the weight vector on each example, right? So we're not looking at all the examples as we did in gradient descent, computing the gradient, but rather we're computing it one by one. And we derive this update rule where at time t plus 1, our weight vector is going to be the weight vector we had at time t minus the gradient of the loss function times some constant, learning rate. This is how we denoted it in short. Right? Again, with the GT is the gradient with respect to W at time t. So now, this is, as you can see, a family of learning algorithms. If you choose Q, a loss function, it will give you one algorithm. Choose another Q, it will give another algorithm. That is another update rule. So let's try it. So what have we done so far with this update rule? We tried it. Okay. Okay. This is something that we've seen. What's happening here? Okay. I think I moved too fast. Okay. Okay, we tried it for LMS. LMS is this loss function here, y minus dot product square times a half. And we computed the gradient with respect to this loss function, and that's what we got. That what we have is the negative value of y minus dot product times x. Okay? So notice that even though we make the prediction based on the sign of the dot product, when we update, we don't care about the sign. We just take the value of the dot product and use it. And therefore, in general, we're going to update every time because y is not going to be the same as the dot product. So always we're going to have something here to use as an update to WT. Okay, so that was the LMS. But I can use other loss function. You know, I gave a few examples for a loss function, and now I want to use this blue loss function here, which we call the hinge loss. So this is a loss function that when the dot product is 1 or greater, it does nothing, no loss. And if the loss function is 1 or below, it grows linearly with the dot product. Remember that the x-axis here, or the z-axis here, is this number, the dot product times y. So this hinge loss is defined this way. This blue curve that I show here, it's the max between 0, and 1 minus the sign dot product. Let's think about it again. So if this guy is very large, greater than 1, which means, first of all, that we don't make mistakes because y has the same sign as w dot product x. If the dot product is positive, y is positive. If the dot product is negative, y is negative. So this is positive. Not only it's positive, it's greater than 1. So it's separated from 0 by 1. In this case, 1 minus this is going to be negative. We're going to be in this region to the right of 1 here, and therefore the value is going to be 0, no loss. On the other hand, as this one goes down, either it's less than 1, still positive, but less than 1, or negative, then this is going to be greater than 0. So the max is going to be the value of this expression here, and we're going to go up linearly with this number. So what I said is that the loss is 0, or the gradient of this function is 0 if this sign dot product is greater than 1, because the value of the function is just 0. Otherwise, the value of the function is this, and the gradient is the negative sign of y times x. Okay? So what does that mean? That means that if the sign dot product is greater than 1, we do not update. The gradient is 0. On the other hand, if I made a mistake, I'm updating according to this gradient, which means I'm taking w and I'm adding to it y times x with some learning rate r. Which means, what is this algorithm? One word here. what is the algorithm that we derived by taking the hinge loss and computing the
Perceptron.
gradient?
Perceptron.
It's Perceptron. So magically, we now presented Perceptron as a stochastic gradient descent algorithm with this loss function, with the hinge loss function. So Perceptron, being a mistake-driven algorithm, is also a stochastic gradient descent algorithm. Now let's think a little bit about, so that's a very important thing. We basically unified what we started with at the beginning of the class with SGDs, with Perceptron, that was invented completely independently as just an update rule that made sense to a neuroscientist that had very, very good intuitions. And then we showed that this is really a stochastic gradient descent algorithm for a very sensible loss function, the hinge loss, that we're going to see a lot of even later. Now, let's play with Perceptron a little bit. I'm just copying what we had before. This is Perceptron. Gradient is 0 if we are good. Otherwise, this is the gradient. Now, let's imagine that I'm looking at Boolean examples. Simplifies our life. So this is the example I'm looking for. X1 is 0, X2 is 0, X3 is 1, X4 is 1, X5 is 0. It's a positive example. Assume that you made a mistake on X. I want you to think about what will happen to W2. W2 is the second coordinator of the weight vector. And also think what will happen to W3. Now, I'm looking at X again, and I made another mistake on the same X here. Think again, what will happen to W2? And what will happen to W3? And let's do it again. So I'm going to ask you this question now. Think about this example, 0, 0, 1, 1, 0. I'm filling it 3 times. I'm always making a mistake on it. And I want to know what will happen to W2 across from X2 here, and what will happen to W3. So think again. Okay, as I'm trying to not show responses for now. Again, the weight vector was 0, 0, 1, 1, 0. And I want to know what will happen to the weight vector when I'm making mistakes. And remember, I always make a mistake on this example. 3 times in a row, I'm making a mistake. Okay, most of you, or many of you have already responded, so let's see what you think. So many of you think incorrectly that A is the right option. Why is this an incorrect choice? Okay, so let's look again at the example. So so X2 is 0, right? So what happens when X is 0? No change. The gradient is 0. Therefore, we're not going to change. So weight that are across from a 0 coordinate do not change. So W2 is always going to be 0. Doesn't matter whether we make a mistake on a positive example or a negative example, W2 is not going to change because X2 is 0. And this you can read directly from here. What happens to W3? I made a mistake here. Now, remember, this is a vector, but I'm only caring now about the third coordinate of this vector. The third coordinate of this vector is 1, and therefore G is going to be 1. Or G is going to be -1. I have this minus here, which means I'm going to increase W3 by 1. It's a positive example. I'm increasing it by 1. What happens when I make another mistake? Same thing. This algorithm has no memory. It always does this. Computes the gradient. And therefore, if I made a mistake, it's a mistake on a positive example, and X3 is 1, it's going to add 1 to W3. So which means in all three examples, C is the right one, right? So W2 never changes, and W3 grows by 1 all 3 times. So that's a good segue to the last thing I want to talk about today, which is a new stochastic gradient algorithm. Now, so far, in all cases, we had a fixed R, a fixed learning rate. And as you could see in the example that I just showed, the fixed learning rate means that if I make the same mistake 3 times on the same example, it behaves the same. It has no memory. Now, we talked at the beginning when we discussed stochastic gradient descent that it would be nice to change the learning rate a little bit, adapt it based on what's happening, maybe make it smaller sometimes. And this learning algorithm that we're going to discuss now in this slide, it's called an ADA-GRAD algorithm for adaptive gradient. And the idea is that we're going to change the learning rate as a function of time. So again, it's a very, very simple learning algorithm. And the motivation is that we want to look at frequently occurring features. And with time, incur small changes to them. While infrequent features that surprise us, we want to update them with higher learning rates. How do we accomplish this? So we define a per feature learning rate this way. So now T is the time, and J is the index into the vector here. Capital G of Tj is defined this way. It's the sum from the beginning of times, k equal 1, until the current time t, of the gradient, the square of the gradient I've seen so far. And the learning rate is going to be a fixed learning rate, think about it as 1 if you want, divided by the square root of this sum. The overall update rule is going to be the t plus 1 weight in the jth coordinate is going to be the t in the jth coordinate minus the same thing as before, right? This is the gradient, and this is the new learning rate. Now, again, the easiest thing to think about is, think about it in the case, think about it in the case of the example I just gave. Think about it in the case of Boolean examples. X2 is 0, X1 is 3. W2 is never going to change because X2 is 0. But this guy, once we make a mistake on it, the first time it's going to be 1. But as we go, this one is going to be 1 plus 1 plus 1 as we go. And this one is always going to be 1, the GTJ. So with time, this ratio is going to go down. And the learning rate, the effective learning rate we're going to use is going to get smaller and smaller. So take the example that I showed in the previous slide that I asked you about and try to compute this other grad on it and see what happens to the jth coordinate when x is 1, x3, for example, is 1 for a few consecutive examples, a few consecutive mistakes. Okay, I want to stop here with the following comment. So AdaGrad is a very important learning algorithm because it's the first one that actually, in a provable way, updates the learning rate. In fact, when we go to neural network, you will see that almost all the update rules that we were using there, all the algorithms are going to be stochastic gradient descent based, and all of them will have a changing learning rate that are based on AdaGrad. If you want to care about other algorithms that are more advanced than AdaGrad, you can follow this link here. Most of them are a lot harder to understand because they involve more sophisticated optimization algorithm, but it's not clear that they are much better than AdaGrad, I mean, which is a very simple learning algorithm. Okay, I'm going to stop here. Any final questions?
One question, Professor. Are these class recordings posted somewhere?
Yes, these recordings are posted on the website. Every day, a few hours after the lecture, the recording is there.
I have a question.
Yeah.
How does the AutoGrad, the adaptive learning rate, affect like how fast the algorithm converges?
So there are theorems. If you go to the original paper of AdaGrad, it shows that it's going to converge faster than Perceptron, faster than other stochastic gradient descent update rules. Now, in fact, this depends a little bit on the type of data you have, but under reasonable conditions, one can prove that AdaGrad is going to converge faster. Hopefully, you will see this in the homework. Okay, so let me just finish by reminding you the administrative slide I started with. We have no class. You have a vacation on Wednesday. And we also extended the due date for homework 2 by 3 days. So it's due now October 22nd. Go to the Piazza message to see the details, or go to these slides that are going to be available in a few minutes on the website. And I'm going to see you, unless you come to the office hours, on Monday next week. Have a good week. Bye.
A quick question. So class recordings, will they be, I looked out there, I wanted to review some of the other ones, but I think it's only up to 9:14. Will there be more class recordings?
I'll check that. It's supposed to be there after every lecture. So you're saying that, no, it cannot be up to 9:14. I think all the lectures should be there until the last one. Maybe update your browser or something like that.
I was speaking specifically
refresh your
about
browser. Ask a Piazza question if you cannot access it.
It's definitely on YouTube.
Oh, they're on YouTube. All right. Yeah, let me take a look then. Thank you.
Okay, thanks.
Thank you.
Bye.